The solutions to the chapter 4 and 8 homework on circular motion. And remember, you do not have to correct problem 41 for chapter 8, because I didn't get the right answer. So if I can't figure it out in a reasonable amount of time, then I don't think you should need to as well. So you still may want to take a look and compare what I did to what I showed on the quick answers, which is from the book. At any rate, 26 is saying an old-fashioned vinyl record rotates on a turntable at 45 RPM. What are the angular velocity in radians per second and the period of motion? So if I have 45 revolutions in 1 minute, that's 2 pi radians for 1 revolution and 1 minute over 60 seconds. So if I multiply those through by 45 times 2 pi divided by 60, that equals 4.7 radians per second. The period of revolution is essentially, if I get 45 revolutions over 60 seconds, then that's 60 seconds over 45 revolutions. That's 1.33 seconds per cycle. You could have also taken 6.28 radians divided by 4.7 radians per second, because 6.28 radians is 2 pi radians. That's 1 full circle as well. Problem 33, saying the radius of the Earth's very nearly circular orbit was 1.5 times 10 to the 11th meters. Find the magnitude of the Earth's velocity, angular velocity, and centripetal acceleration. I think we went over this in class, but essentially what I've got is 2 pi r over t. So 2 pi r, that's the circumference, that's the time, and then I convert days into seconds. So I get around 29,900 meters per second. Angular velocity is just 2 pi radians over that same number of seconds. So that's 1.99 times 10 to the negative 7th radians per second. The centripetal acceleration, you could do this either way, omega squared times r or v squared divided by r. Either one doesn't matter. So that should give you 0.0060 meters per second squared. Problem 38, I think, is super useful. It relates back to kinematics things that we've done. So I've got a uniform acceleration here and a uniform velocity here. So the displacement is the area of a velocity time graph. So the angular displacement is the area of an angular velocity versus time graph. So I just take a look at this triangle and this rectangle, and I get that that's 60 radians, but it asks for this in revolutions, so I convert 60 radians times 1 revolution over 2 pi radians, and that's 9.5 revolutions. So that was kind of a nice one. Chapter 4, problem 41 and 46. So 41, it's a bicycle wheel which was rotating at 50 RPMs, and the cyclist began to pedal harder, giving the wheel a constant angular acceleration of 0.5 radian per second squared. What's the wheel's angular velocity 10 seconds later? So this is just using a kinematics formula. So first of all, I converted this to my initial angular velocity of 5.24 radians per second. The acceleration was 0.5 radians per second squared. So I figure out the final angular velocity. And then it says that you want to convert that RPM. So once I get 10.24 radians per second, go back to revolutions per minute. So I don't know a quick conversion for that, but I do know how to convert seconds to minutes and revolutions to radians. So for part B, it's asking for how many revolutions the wheel makes during that time, so that's angular displacement. So again, I use my angular version of the kinematics formula that we've used for a long time, and I get that this is 77.4 radians. Again, 77.4 radians times 1 revolution over 2 pi radians is 12.3 revolutions. The book answer to this, I think, was incorrect, by the way, so I think my answer is correct on this. And oddly, the book answer to this one, I think, was correct, to part B. Problem 66. We're saying astronauts in a centrifuge. The centrifuge takes 30 seconds to speed up to its top speed of 1 rotation for every 1.3 seconds. The astronaut's strapped into a seat 6 meters from the axis. What's the astronaut's tangential acceleration? So basically, we're going to go from 0 into 4.83 radians per second. So that ends up being 29 meters per second. And so now I can just do 29 meters per second divided by 30 seconds. That's 0.97 meters per second squared. So it says tangential acceleration, so we need meters per second squared. So the linear speed starts at 0. The final linear speed on the outside of the circle is 29 meters per second. So basically here all we're doing is we're converting angular velocity to linear velocity. For part B, how many g's of acceleration does this have? So if you're moving 29 meters per second, the radius is 6 meters, we have 140 meters per second squared. That's our centripetal acceleration. And it's 9.8 g's for 9.8 meters per second squared for 1 g. So this is around 14 g's. I don't know if that's survivable for a long period of time. I think for a very short period of time it may be. Okay. Chapter 8, problem 13. I think we went over this in class also. The key thing here is the centripetal force acting on M1 is equal to the gravitational force equal on M2. So that's the big idea, balance forces on M2. So then I can treat this as M1 V squared over R, M2G, rearrange that, and that's how I solve for it. That's a nice problem. Number 25. Said a 500-gram ball swings in a vertical circle at the end of 1.5 meter string. When the ball is at the bottom, the tension is 15 newtons. So the key in this case is recognizing 15 newtons is not the centripetal force. 15 newtons is the tension pulling up, but gravity is pulling down. So the centripetal force is, which is what you need to maintain that circular path, is 10 newtons. And that's equal to 0.5, which is the mass, V squared over R. Okay, so this free body diagram here is super helpful. This is the one I boogered up, so I'm not going to go over it because I boogered it up. But essentially it says a concrete highway curve, radius 70 meters, banked at a 15-degree angle. What's the maximum speed at which it can rubber-tired car can curve? I got 29 meters per second. It should be 34. So I think I coast when I should have tangented a couple places. So essentially, I was thinking about it like this, saying that's the normal force, but then that is now acting as the, when you're pointing up, that is actually acting as the hypotenuse, whereas acting downwards, the gravitational force is the hypotenuse. So got to think about an inward component and so forth. And I think I have a general idea. The friction plus the normal component is equal to the centripetal force. Oh, but here's what I think I did wrong. I think it's only the inward component of friction plus the inward component of the parallel force, which equals the centripetal force. So I think I didn't take this completely into account. That's what I think happened. Okay. Problem 51 was this amusement park ride. I went over this. So it's a vertical circle. So the key thing here, once you know, you got to have the radius. Essentially, you can figure out the centripetal force for this person of mass, 55 kilograms. You can figure out the angular velocity. It said it took 4.5 seconds to go in one circle. So if I know the angular velocity is 1.4 radians per second, centripetal force is mass omega squared times r, so that's 862 newtons. That would be true at the top or at the bottom. So at the top, gravity is acting downward. At the bottom, gravity is still acting downward. But at the top, the centripetal force is acting downward. At the bottom, the centripetal force is acting upward. So therefore, the normal forces are quite different. So take a look at this for how you would get the answer. And I did round 2 pi to 6.28. So to prevent the riders from falling off, at the top, the centripetal acceleration would need to be at least 9.8 meters per second squared. So this really should be greater than or equal to 9.8. So that means this should be greater than or equal to 1.11. So the minimum angular speed be around 1.11 radians per second. So if it's 1.11 radians over 1 second, that's 2 pi radians over what time to go around a full circle? Around 5.7 seconds. So hopefully those help. And